So, hi everyone, my name is Joakim Bech, and we have Jens here also presenting with me. So this is a BoF session, so we would like to get some feedback on the idea of using device tree in firmware, something that we have starting to use a little bit in Opti. So, hands up, how many know what device tree is here? Right, so probably no need to go through this, but it's a binary representation of the device itself, basically. So we have seen that firmware is, you have more firmware in the running in the devices today, and just as Linux kernel, there is some need for having the same kind of thinking that you would like to have one binary and you have the configurations separately. And that is what we have been looking into here also. And we can see here that the firmware components we have listed here is the T, we have the monitor, we have UEFI, U-boot, grub. So there's quite a few things running before you hand over to Linux kernel. And the use cases we have listed here is what we do. We reserve some memory for the secure side. You eventually want to reserve some peripherals. You own that from the secure side. And boot arguments and such. So the same kind of use cases, more or less. This is what we are using today. So U-boot is quite obvious, and UEFI also, I guess. I'm not that into UEFI. From Opti, we use it to, we have a node to tell the kernel that Opti driver. So the Opti driver will find the secure side and know where to pull things from. And we also use it to reserve some memory. That's the use cases we have. From untrusted firmware, Jens added some fix here for the PSCI nodes, and that's to bring up the CPUs and so on. And the flow that we have is described here. So untrusted firmware takes it, it gives it to Opti, and then gives it to UEFI or U-boot, and then to the kernel. So that is very short introduction of what is done and how we're using it and so on. And now we would like to have some feedback. What do you think about it? If this is the right way to do, should it be done in another way? Some questions here. Where should the DTS files be? Should we have them from kernel and pick them from kernel, or should we have them separately? And questions like that. And I've seen also on the forum, Dan probably, there was some engineer saying that it might be overkill to have libftd in boot binaries and so on. So there are several aspects here that we would like to get feedback on. So any comments? Grant. I guess you were.
What is the queuing loop pattern?
So when QEMU starts, it generates a DTB, which is stored in RAM, and untrusted firmware finds that and does the updates for PSCI, and also passes the pointer to Opti when Opti initializes, and Opti adds its nodes and memory as described, and returns back to untrusted firmware, which in turn launches UEFI. UEFI on QEMU knows that the device tree blob is at a certain location in memory, so we didn't have to pass a pointer to the DTB, but on hardware we would probably pass this pointer instead of relying on a hard-coded address. And the rest is the usual flow.
So that goes hand in hand with this read from flash once. That is probably quite nice, and then just hand it over as a separate part.
I guess the other thing that's worth pointing out there is that if you're doing this and then you've got CAVium and so on, and you're eventually running UEFI, then UEFI will construct its ACPI tables by asking QEMU for a bunch of ACPI table fragments. So it's not the case that the DTB is the only source of truth about what the system looks like. So if you're going to apply this to hardware, then the question is, are you then going to try and generate all your API tables from the original DT thing, or is there some other setup you have there?
Well, so far we haven't really thought about that, I guess, so that's a good comment.
So I guess we're using, CAVium is using, in our firmware, using just our own private DTB, so not Linux bindings, but just, it's a data format. We're not going to, didn't reinvent that. So we're using, for our own stuff, describing some hardware as well as some, you know, configuration, which I know generally isn't, you know, that's not how Linux uses it. But, you know, yeah, right. So I mean, so we have, you know, we actually have for our, you know, even before ARM trusted firmware, we actually have two separate DTB blobs. One is for the manufacturing info for a board. So that's like where MAC addresses and serial numbers goes, and that's write once at the, you know, never updated. And we have then another DTB that actually then describes the hardware that the firmware wants, and the first level firmware combines those and passes that then, you know, up the chain. So we've found that to work quite well, and so we have it like an ARM trusted firmware port. You know, we use the DTB there already, and then that gets, and this is all separate from some of that stuff, like the MAC address will filter its way up and then be added to the real Linux DTB. So.
This is something that is just done locally on your side?
Yeah.
Nothing is found, okay. So do we know if, maybe Rob or Grant, do you know if we had discussions like this in the open?
And I guess maybe just one side thing I want to bring up is the sort of on the configuration. I mean, I think that this could be useful for not just the hardware description, but for like if you want to configure, well, selecting options in, you know, how ARM trusted firmware runs, not just telling it about the hardware, which is useful too. But I think that there are things of where you might want to, you know, where that's not how it's used in Linux, but I think that that could be you know, a useful use for it in firmware.
I mean, generally, using libfdt, using DT in firmware is, I mean, it's a reasonable approach. It is just a data structure. You need to pass data from between these various firmware components, and having a structured data to do that makes sense. The caution or the guidance I would give on that is take the time to think about and write down what information it is that you need to pass around, because it can easily get to, you build very big DTB files, and you know, the more complicated you get things, the harder it is to audit and figure out what you're doing. So I would recommend really defining what the model is that you're trying to do. And if opt is only touching a small subset of the hardware, to restrict the DTB that it receives to just that data is probably reasonable. So.
But then there is also these secure prefix bindings that were upstreamed by Peter. So that's supposed to be used, I mean, the secure status. That's supposed to be used to be spread over the whole kernel DT, basically. So that, how do you handle that?
It's been a bit since I've looked at the secure binding, so I can't at this moment. When I'm also feeling very ill this morning, I don't remember what things are there. Rob would be able to answer better.
Right now what is there is just purely the secure status, though it is designed to extend to other properties, and that's purely just for partitioning of peripherals. And I would consider that pretty minor changes to the DTB. So what's the concern with whether libfdt is an overkill? The size of it, or?
So, yeah, just to firstly just echo what Roy was saying about it, the initial use case we saw in within the firmware itself, trusted firmware, is for configuration of the firmware, not actually some kind of full hardware description to do full probing and things like that. But the specific concern here was more in the runtime aspect of trusted firmware. We didn't like the idea of there being a device tree that gets parsed at every single stage of the boot process. So the runtime part, there's concerns about size of the code. Many partners want to keep it as simple as possible, so we'd prefer any parsing to be done in the kind of transient boot stages, and then some kind of in-memory representation passed to the runtime firmware, or at least have this as an option, so not all partners are forced into this overhead.
So I think runtime-wise, it's fairly tiny. Part I worked on in the past kind of did the same thing. It wasn't really trust zone, but it was a microcontroller on the chip. Read the DTB from flash, added in MAC addresses and various configuration that only the microcontroller knew, and then passed that to the A cores, and then it was U-boot at the time. And it was 5 or 10K, I think, that it added.
Yeah, that's not small in our world, unfortunately. Every K counts.
Sure.
So depending on your goal, and I missed the first couple minutes, the Zephyr guys at ELC had a nice talk about how to do device tree with a release memory constrained model, where they basically take a device tree. So their goal is probably different from what you're describing, in that you want to have only a single piece of configuration of describing your hardware, because once you have multiple ones, things will always go bad because they're getting out of sync. So they basically wanted to make sure that they have one device tree that basically just describes hardware, and they can just use that wherever. That one device tree basically would go and get parsed in the build process of the firmware. So you would take it as an input file and then build defines in your header files and just basically use them. Depending on the problem that you're trying to solve, that might be a viable solution, right? If you really do care about like 1 kilobyte, you usually do know what hardware you're running on.
And the other thing I mentioned here also, I'm not sure if that's a big deal or not, but where to store the DTS files. If you read something in Linux kernel and you boot it up and you check it in proc and so on, then it might look different. And that since someone has already done something in firmware, and I'm not sure if that's a big issue or not.
That already happens because U-boot changes That already happens because U-boot changes the device tree to some extent.
So it's okay to do it.
If things are dynamic and the firmware needs to fill it in rather than it being in the DTS, then that's fine.
You've also got a different threat model than the kernel has to. I mean, we've shipped DTBs with the kernel because it turned out it was convenient, but you don't want to be replacing, if you're replacing the DTB that gets passed around to firmware, that's a major attack surface. And Tixie wants to weigh in on this. But yeah, so that alone is an argument for, okay, how does where's the DTB stored? Who trusts the DTB? And is there any signing? How is signing applied to the DTBs that firmware's using?
I just wanted to jump in there because you're saying, I understand that there is a security implication, so, but the system is a whole thing, and when you're putting the system together, you don't know all the pieces. So the people working on the firmware, the people working on the operating system kernel, you haven't got a complete representation of the system integration. It's when you put the system together from pieces. So you do need a method of updating these things. So if you can't put configuration in, if you can't put information into a device tree that the kernel requires to work optimally, because that might compromise secure firmware. You need a way of adding it in extra. That's all I'm saying is, you need to be able to update your device tree for the sort of higher levels. So you need some method of that. You can't just say firmware provides it, and then ultimately that filters through to Linux, and it's got no, and you've got no control over it. You need a method of being able to inject things, whether or not that comes in at a higher level, to get this extra information in. But it doesn't mean then you don't have one representation.
So I agree on that with the kernel device tree. For the use cases I see in the firmware side, it would be a very closed internal representation configuration within the firmware, which would be part of the chain of trust in the firmware, and wouldn't kind of. I don't see, you know, the value of a single device tree that gets passed around and manipulated through all stages of boot through this firmware into the kernel like this. I think it needs to be a standalone thing, at least to start with, until we understand how what information does need to pass through those different boot stages.
What about the example that Joakim gave, the memory reservations and so on, the fact that Opti needs to declare that it is actually present and initialized so that the kernel will start the driver and probe using SMC or anything. That's kind of information that you have to pass from the firmware to the kernel. So if you have two DTs, that rules out this mechanism. So no.
No,
Yeah.
but what it does mean is it means you need to define how you do that. If you've got a kernel DTB, it doesn't change the fact that configuration of the secure world and what devices the secure world takes responsibility for, it's going to need to be passed. So that's one of the areas where you constrain your configuration, and you say the behavior here is firmware will look for these nodes and will modify them as appropriate. And you draw a box around that, and you say, look, this is the interface. So it's more, the DTB is just a data format at that point, because equally important is the behavior that is standardized for that platform.
Right. I think we're about to end actually already. 4 more minutes. I think we've got some ideas, and it seems like we need to have a second look at this and look at both security implications and what and why we need to do it. And we should also
keep in mind that U-boot is actually moving to exactly that model where it's using the same device tree everywhere. So in U-boot, every new board that comes in has to have the kernel device tree, and this includes that, and then annotates it with a couple of more properties to basically say these are devices that you need to have early in U-boot.
Right.
That is a very good documentation about a control DTB. Is that right?
That is the one. Control DTB is
It's just one DTB that.
the control. So the control DTB, in modern U-boot, the big picture of that is you basically have the control FTT in U-boot, which is a device that gets included on build time of U-boot, that then goes and initializes internal device model objects inside of U-boot to be used while U-boot is running. And U-boot these days also can do EL3, so you can even go and do your PSCI provider in U-boot with configured all by.
The same DTB that is passed to the kernel, or is this for just U-boot's internal consumption, and then there's a different
U-boot never forces anything on anyone, right?
Okay.
As you might be well aware, but the final goal of this, and a lot of architectures or a lot of platforms do this today, should be that this is the same device tree that Linux also uses. So, for example, the distro boot code in U-boot uses the device tree, the internal device tree, as a fallback if it doesn't find a manual override device tree on the disk device that it's trying to boot. Which means by default, it will use that internal device tree, and that works just fine. I mean, we are actively pushing a couple of vendors to that model. So everybody we are working with, basically, because if we want to boot from a U-boot model, we do need to get the device tree from them, and that same device tree model is the sanest that I can think of, since you don't want to have two device trees in different areas somewhere lying around and diverging. And eventually, it's much easier to just make U-boot use the Linux kernel bindings, the Linux device tree bindings, and everything just works out of the box. So I honestly don't see the issue where it would be an issue to just use the kernel device tree. Worst case, you just annotate it and say this is a device you shouldn't care about right now, because I don't want to have it initialized in early firmware, or this is out of scope or whatever. Right? You can just add those, or as long as you have U-boot or bootloader specific properties, just add them in parallel. Linux will just ignore them. You don't have to push that device that you use for both for firmware and for kernel. You don't have to push that into the Linux kernel tree. It's a different thing, right? As long as the Linux kernel device tree is a full subset of whatever you have in your full system, everything just works. You use a few things for your firmware, and then everything else goes there, and Linux ignores the piece it doesn't know about. Done.
Well, from a maintenance thing, then you're constantly merging. You've basically forked the kernel device tree. I mean, in terms from a maintenance point of view, if something changes in the kernel device tree, now you have to get those changes, integrate your changes on them.
No, the kernel device tree does not change. It should not. Well, you're doing it wrong. If you're doing it, you're doing it wrong, basically. If you change the kernel device tree incompatibly to what it was before, you're breaking every kernel that was running before, which means we don't care about your system.
Yeah, it's not just new features and new bindings get added. So yes, in theory, it's binding compatible. It's not always, but even without the compatibility issue, if you ship new kernel, it's got new features. It supports new OPP bindings and stuff like this. Lots of power management features, or support for opt-TE. Well, it means then you have to update the bootloader because it's got the device tree in for the new kernel, or opt-TE in. U-boot will then need to know about opt-TE in order to modify its device tree it's passing to the kernel. So, so U-boot's going to be control of everything.
All right. Sorry, guys. Yeah. We are about the time is running out, so we have to call this. Thank you for the feedback so far. We will see if we will follow up. In some way, we will follow it up at least, because we are working with it already. But thank you for all the ideas that you got.